Good morning. In the last lessons, we have learned something about the troubles for the body of an astronaut in the absence of gravity. We have seen that there are some problems in both the neurovestibular system as well as in the cardiocirculatory system. We have seen also some possible countermeasures, which are only partial. And today we want to see which kind of problems are encountered in the musculo-skeletal system in the absence of gravity, or better, in microgravity. First of all, let's give a glance to the structure of both the muscle system as well as of the bones, just to enter into to the problem. First of all, the muscles. Not all the muscles are skeletal muscles, but certainly the skeletal muscles are very important because they are the largest muscles which can form up to the 40% of the total body weight. And these muscles are able to contrast gravity and therefore work every day in almost every moment for a lot of function we perform without thinking about. For instance, springing or lifting weights or even simply standing, we are working against gravity. And therefore, both bones as well as these kind of muscles are solicited. Of course, not only the muscles are skeletal muscles. We can think only simply to the heart. The heart is a muscle. It is not attached to bones. But nevertheless, these muscles, as we will see, suffer atrophy in the absence of gravity. And we want to see what are the main troubles and the corresponding possible countermeasures. Here in black, you can observe the main postural muscles. The structure of the muscle, the fundamental unit of muscles is a cell which is called myocell or simple fiber. The structure of the fiber is a filament which has a diameter of about 50 microns. Imagine more or less the same diameter of an hair. And it contains a lot of myofibrils and mitochondria. Mitochondria are essential in order to produce energy inside every cell. They are a source of plant sources for energy because they supply ATP. And therefore, it is not surprising that many of them are concentrated inside the corresponding muscle cells. And inside the myofibril, there are a lot of filaments called myosin and actin. They are essential in order to produce contraction of the fiber and correspondingly of the muscle. And beams of these structures form the macroscopic muscle. Of course, the increase of the muscular mass is due to genetic factors, of course, because everyone has a different body structure to any other. But it is important to point out that training is essential both for increase the number and the size of the fibers, at least in certain period of our life, youth typically, but also to maintain in activity the fibers, because otherwise the muscles tend to be atrophied without suitable exercise. Concerning bones, we are accustomed to think about our skeleton as a static structure. This is not true because a skeleton is a completely dynamic structure in the sense that in order to have good bones, these are continuously destroyed and remodeled in our body. And first of all, the structure is a porous structure. Why porous? Because this tissue must not add too much weight to our body, and therefore it must be as light as possible, and at the same time it must contrast stress. It must offer strength, and therefore we can observe that it is composed by both by collagen fibers, which are needed in order to supply elasticity, and minerals, mainly calcium crystals. They supply strength. And these bones are continuously built by specialized cells, which are called osteoblasts. Osteoblasts provide collagen and control the mineralization of the bones. When the bone is becoming old, it is substituted by new tissue, and to this purpose, osteoclasts, another class of specialized cells, provide to partially dissolve the mineral and counteract the bone formation. And the equilibrium is granted by adding a third class of cells, which are the osteocytes, which are able to both synthesize and remodeling the bones. And they are essential in order to preserve this dynamic equilibrium. Bones are the main storage for our body of calcium, because more or less 99% of the calcium is contained inside our bones, but we should not forget that calcium is also essential for various fundamental properties of cells. For instance, it is used as a cell messenger by almost every kind of eukaryotic cells, not only the cells of our body or also of our animal, but similar messages are transported by calcium also in plant cells. So it is a fundamental function. For this reason, it is important to grant equilibrium, homeostasis of calcium in our body. And due to the fact that they are continuously remodeled, in adults, every 3 to 5 years, more or less, the whole structure of the skeleton is replaced. And there is a balance of bones, because, of course, when we are young, the balance is positive in the sense that we increase the bone mass. When people are getting older and older, the bone mass is lost, essentially for demineralization. And this balance declines at later ages, after 35, 40 years old. There is a decline in the sense that there is a decrement of bone mass up to 2% per decade, usually. This amount is faster for women due to hormonal factors. Within 8 years after menopause, women tend to lose calcium faster than men, and this decrease can amount to up to 2% in some cases, of course, per year. But I point out that the decrement regards tens of years. Okay, and in this picture you can observe the behavior of the bone density as a function of the age. The bone density decreases after 40 years, and there is a slow decrease. And below a certain level, we call about osteoporosis, which is a disease of which many millions of people along the earth are suffering. And we also point out that in the case of an astronaut performing a long travel in the absence of gravity, typically a few years, 2 to 3 years, the decrease is much faster. And the risk is to have, after landing again on the Earth, an astronaut in the middle age of his activity with the same demineralization of bones as in old people of 80 years. We will come back later about this problem. Of course, the demineralization offers the possibility to less strength to external stimuli, and therefore the risk of fracture increases with age. There is a disease for bones, which is called osteoporosis. We do not know the cause, and there is no care about this disease up to now. But especially women, but also men are suffering by also osteoporosis. And in this picture, you can observe the difference between a normal porous tissue on the left and osteoporotic tissue. We can see how much more fragile is the structure. And apart from genetic factors and also probably environmental factors, physical activity is an effective, somehow effective countermeasure to contrast, at least partially to contrast osteoporosis. And what about absence or microgravity? The exposure of microgravity stimulates both muscle atrophy processes as well as demineralization of bones. Concerning the muscles, this can be monitored by looking for the nitrogen compounds in urines of astronauts. It is observed that during the flight there is typically an increase, a significant increase of excretion of these compounds with respect to controls on heart. And this is particularly significant in postural muscles. This is a first way to monitor the loss of muscle mass. And another typical measurement is to measure the leg circumference for an astronaut. You can see an astronaut undergoing this control. And we have seen that partially the reduction of the leg circumference is due, especially in the first days of the flight, to a redistribution of blood fluids inside the body. There are less fluids in the legs, and therefore the leg tends to be shorter. This is the so-called chicken leg syndrome for the astronaut. But this is a process interesting the legs in the first days, and the processes continue after weeks and months. And the longer is the mission, the higher is generally the reduction in the leg circumference. And this is also another important indicator. Also, a decrease in the protein synthesis is observed, which can amount up to 15%. Of course, this number depends and can vary from individual to individual. And of course, this weakening of muscles, especially locomotion muscles, can give risks to locomotions, not only when the astronaut come back to Earth, because they are helped, of course, but especially in provision of a long travel mission to Mars. There are no hospital, and therefore they are going against some risks because of course, they are expected to have also heavy activities on the Mars soil. The bone loss in microgravity amounts to up to 2% per month, to be compared with the number before. And this decrease is not homogeneous in the whole skeleton, because there are parts of the skeleton which suffer higher decrease, other which are not suffering at all. And in this picture, you can observe that, for instance, in the case of arms, the bone loss is not significant, and the main losses are found in the leg, in the pelvis bones, as well as in the spine. And this is also not surprising, because as we know, legs are not useful for astronauts in order to move inside the spacecraft. They float in the air, and therefore they swim in the air, and they mainly preferentially use arms and fingers, and therefore they keep arms trained both for muscles as well as for bones. It is significant that the loss of muscular mass is measured from the legs and not from the arms. And it is important to point out that this process is not arrested after landing, but it continues. There is a sort of hysteresis and can continue up to several months after returning to Earth. Of course, the amount of time depends on the length of the mission, the duration of the mission. And bone loss means mainly calcium loss. And this has also important, although indirect, effects, for instance, on kidneys. Because if there is an increased excretion of calcium, this means that the kidneys must work heavier than normal, and there is the possibility to increase formation of stones. This, of course, is not a problem on Earth because we go on the hospital, but think about a long-term mission and an astronaut suffering of stones. This could be a catastrophic situation inside the spacecraft, not only for himself, but also for the other crew members. And we have to point out that also other bone tissues are affected, and we have seen that the spine decreases, and in the spine there are also bone marrow tissues, and this also can have possible consequences, for instance, for the blood formation. So the problems are interrelated and must be carefully evaluated before a long-term mission. Okay, in this picture you can observe in black what I have already seen, that is the main bones interested to this progressive demineralization. And of course the bone loss increases the risk of fracture, which in some cases can arrive to 5 times with respect to controls on Earth. And think about the risk concerning activities which require particular strength workload, like, for instance, extravehicular activities. Of course, the solution of this problem would be very important for a space mission, but could have positive consequences also for all the people on the Earth, which for a reason or another, there is not osteoporosis, of course, suffer of disease on bones and lose calcium. And of course, after landing, an astronaut start to recover the situation pre-flight, but this recovery is longer, the longer is the space mission. Up to now, we can observe that with some astronauts, the complete recovery requires up to 3 years for a mission of 6-9 months. We have seen a few methods to measure the muscle loss. An intuitive method should be to measure the mass of the astronaut. And of course, if the astronauts lose muscle loss, he should have less mass. And obviously, on the Earth, we can measure the mass by standing on the balance. We cannot use a balance in the absence of weight, because the balance does not measure the mass, but the weight. And therefore, how can we measure the total mass of an astronaut? You can remember that if we attach a mass to a spring and we let the system to freely oscillate, the period of oscillation is related to both the constant of the spring as well as to the mass. And therefore, by measuring the period of oscillation and knowing the features of the material forming the spring, we can measure indirectly the mass. And this is the method which is used, for instance, on board of the International Space Station. There are different apparatuses. On the left, we observe an American astronaut, on the right, a Russian astronaut, but the principle is the same. They are soliciting a system of springs, and the system reacts by oscillating, and the period of oscillation is measured. And in this case, it is possible to monitor every time, every day, over every week, every 3 days, the mass of the astronaut, and correlate this loss of mass to the other methods, like, for instance, the increased concentration of nitrogen compound in the urines. We have talked about the protein imbalance. The reasons for this imbalance are not clear. Surely a partial reason is due to the decreased stimulation of some muscles, but this is not the complete history, because surely there are also genetic factors which are elicited by the absence of the signal of gravity. But unfortunately, we still do not know the factors which are stimulating the genes which are proposed to build the fibers of the muscle to work properly. Of course, also for bones, the genetic factors involving the demineralization are still unknown. And again, useful models can arrive from ground using the so-called long duration bed rest. Apart from the patient which are compelled to remain in bed for several months due to some kind of disease, illness, also volunteers are very, very useful. We have seen this method for cardiocirculatory system, and we can use the same method also for this demineralization, as well as loss of muscular mass, because we can observe that for patients compelled in bed, there is an increased excretion of both calcium as well as proteins. And the effects are very similar to those which are found in the case of astronauts. There is, of course, an increase of content of calcium in the urines, which stabilizes after a few weeks of flight with respect to the control pre-flight, but you can observe that there is a significant difference outside the error bars between the content of calcium during the flight, even after 3 months, and in pre-flight. And a similar situation and similar levels are also found for patients standing in bed for several months. So again, this is important for both kind of researches, both for spatial flight as well as for medicine. What are the possible countermeasures? We have seen that physical exercise is very useful. Also, in this case, we must use physical exercise. Of course, in the case of cardiocirculatory system, astronauts are requested and recommended to perform aerobic exercise almost every day, at least 4 to 5 times a week. In this case, we have also physical exercise, but endurance, resistance, anaerobic exercises. This is the most effective countermeasure. In spite of this, in spite of the fact that astronauts perform a lot of exercises in the International Space Station, the demineralization as well as the loss of muscular mass continues during the flight. And we don't have any indication that they reach a plateau. So this is the big problem, because we cannot extrapolate the results from 6-9 months to 3 years mission. In this picture, we can observe that exercises are in some cases very similar to those which are found on art. Here they use the same instrumentation. In some cases, the instrumentation is similar but not identical, because of course, since the astronaut is floating, he must be constrained by handles or a similar structure in order to perform exercises. Otherwise, it is not solicited. We have seen that for aerobic exercises, they mainly use a treadmill as well as a cycloergometer. It is possible also to organize, for instance, the treadmill in order to produce both aerobic and resistance exercises. It must be suitably equipped, and here is an example. There is a special treadmill, at least there was. I don't know if it is still working, but a few years ago there was a special treadmills on board of the International Space Station, which combines aerobic and resistive exercises. It is called the Combined Operational Load-Bearing External Resistance Treadmill. And the acronym is Colbert, in honor of Stefan Colbert, who was very glad of this acronym. He is a very popular TV host. He declared, "I've always wanted to be an astronaut, and I already started getting used to weightlessness. I've let my muscle atrophy for 46 years. And you can observe other kind of exercises which are very similar to those performed on art. Of course, these exercises are important for the fitness of muscular mass, but also for bones, because bones are solicited by means of this kind of exercise, which are characterized by low frequency, because they are performed once every 3, 4, 5 seconds, and high magnitude. And this induce strains due to mechanical loads. And it is also interesting to observe that some scientists have proposed that another kind of stimulation could help as a countermeasure for bone demineralization, that is to apply still stimuli, but characterized by low magnitude and higher frequency, in the sense that using, for instance, in experiment involving sheep, on art of course, sheep were subjected to a vibrating platform in order to induce stimuli of a frequency of about 30 Hertz for a few tenths of minutes per day, and this animal showed, with respect to the controls, an increased bone structure, as it can be observed in this picture. This is the bone structure for animals subjected to vibration and without. There is an increase in the formation of bones. So also this must be better investigated in order to understand if it can be applicable to also applied also to humans. Concerning nutritional recommendation, we could in a naive sense think that if we lose calcium, we should have an increased intake of calcium. But this is not correct, because if the body get rid of calcium, it means that it does not have need of more calcium, and therefore an increased intake of calcium in this condition means only an increased excretion of the same calcium, and therefore more work for kidneys. And the same is for proteins. More or less we need for a body of 70 kilos. Normally, due to the due to the recycling of proteins, we need about 70 grams per body per day. And this is the recommended quantity also for astronauts, because performing exercises does not mean that they need more proteins. It means that they need more energy, and therefore overall carbohydrates, but not a lot of proteins more. And the same indication are recommended also for present diets, also for athletes. Of course, there are also pharmacological countermeasures. There are different kinds of drugs which can be used. For instance, the parathyroid hormone, it stimulates the reabsorption of bone minerals and seems to slow down the excretion of calcium by conserving it into the blood. And a similar action have also other drugs. For instance, beta blockers. Beta blockers are used for a great deal of problems, of troubles. And it seems that they could help to prevent also bone loss. And osteoprotogerin is another regulator of bone metabolism, which could prevent calcium desorption. These studies are made mainly in animals, typically in mice, and in order to be transferred to humans, we must be careful because, first of all, each one can react individually, and therefore it is difficult to find a countermeasure which is valid in general. And furthermore, they may be not only short-term but also long-term collateral effect. For instance, in the case of beta blocker, we know that beta blockers are used in order to decrease the heart rate. And therefore, think about an astronaut which is not tachycardic but bradycardic per se. And in this case, use of beta blocker could be maybe very useful for bones, but it could have a negative influence on the cardiocirculatory system. So we must be very careful to use pharmacological countermeasures. Up to now, the fitness is the general method which is mostly indicated in order to decrease the rate of loss of both bones and muscles. It is also interesting to observe that since our body is quite complicated, there are several systems which are interrelated. Studies in animals which have suffered of vestibular lesions have shown that there is also in these cases a bone loss which is similar to the effect induced by the presence of microgravity. And this could be due to the fact that, as we have already seen in a previous lesson, the vestibular system could indirectly influence also the bone loss because it interacts, you remember, with the sympathetic nervous system which control the bone remodeling. And therefore, since we have seen that microgravity elicits signals inducing a wrong response in the vestibular system, also this could be a possible reason of a stimulation of bone demineralization. Okay, we have seen different kinds of troubles. We have seen different possible activities in order to counteract this problem. Of course, we can think that this problem could be completely solved by using a system supplying an artificial gravity to astronauts. Why not to use artificial gravity? In the presence of long travel, we are sufficiently far from the Earth so that our gravity is greatly reduced. Therefore, is it possible, the question is it possible to induce a pseudo-gravity, an artificial gravity. This could solve all these troubles. And the artificial gravity could be due by means of a centrifugal force. Why centrifugal force? Because apparent forces are equivalent in the sense of general relativity to gravitation. Let's think about this thought experiment which was proposed by Einstein. Thought in the sense that it cannot be carried out, but it can be thought. Imagine a lift standing over the surface of the earth, and there is a passenger inside this lift. And this lift is standing. And suddenly, imagine to remove completely the earth. So this means that we remove the gravity force. In this case, the passenger would float inside, would be without weight inside this lift. Okay. Now imagine another situation. The lift is above the surface of the earth. The earth is not removed, but we break the rope which takes standing the lift. The lift free falls along the gravity force due to the presence of the earth, and in this non-inertial system, the passenger is without weight in its system. This is a demonstration that apparent forces can be not distinguished by the gravity, in the sense that a passenger inside cannot recognize if the rope has been broken or if the earth has been thrown away. Okay, so it is possible to introduce a compensation of gravity using apparent forces, and among the apparent forces, the most simple to use is the centrifugal force. So the idea is to use a centrifugal force in order to simulate gravity. The centrifugal acceleration, you know, is given by the product of the distance with respect of the rotation axis times the square of the angular velocity. And in this diagram, please note that the diagram is not linear, is in a double logarithmic scale. We can observe the gravity level reached for a given radius as a function of the angular velocity, that is the number of revolution per minute. And we can observe that, for instance, if we are inside a small centrifuge, let's say 2 meters of radius, we can reach the corresponding level of gravity on Earth. It is measured in g. That is, 1 means the same gravity level as on the surface of our planet. For 2 meters of radius, we can reach the gravity level by using a centrifuge which is rotating very fast, because we need at least 20, roughly speaking, 20 revolution per minute. If we use a larger centrifuge, let's say 20 meters, 10 times the radius, the level of angular velocity is much less, is of the order of 6, 7 revolution per minute. So it means that it is possible, using different kind of centrifuge, to have a pseudo-gravity according to the size of the centrifuge as well as of the angular velocity. There is a problem, especially in small centrifuge. As you can see in this picture, when the centrifuge is rotating, if the astronaut has his head near the rotation axis, it suffers an acceleration which is quite low because it is very near. R is small, but his or her feet are far away from the rotation axis. So it means that his body undergoes a pseudo-gravity acceleration, a centrifugal acceleration, which is different for the different parts of the body. And we call this effect gravity gradient. And the gravity gradient induces sickness in the astronaut, and the sickness is higher, the higher is the gravity gradient. Of course, the gravity gradient is smaller, the higher is the radius for a given angular velocity. And we have to take into account this effect in the case we are projecting a small centrifuge. We can call, is it needed to reach a gravity level equivalent to the gravitational acceleration on Earth? Is there a minimum gravity level? Yes. Studies performed initially by Russian scientists and later performed also by other spatial agencies have pointed out that it seems that already 0.3 g is a sufficient level to acquire beneficial effects. But of course, these studies are taken for subjects for a short time, not for a long time mission. And the tolerance to gradient is not very well investigated, and more studies are needed in order to have a definite answer to this problem. And unanswered questions is the exposure to an intermittent and high gravity level gives the same beneficial effects as a continuous exposure to 1G level. So we could think to subject the astronaut for 1 hour a day, half an hour a day, to a small centrifuge. In spite of the gravity gradient, we can subject it to an equivalent acceleration of, let's say, 2G on the average. Is this sufficient to counteract the negative effect of the lack of weight? We don't know for the moment. And gravity levels below 1G, for instance 0.38 G, are effective in order to contrast the negative effects on the health of the astronaut of the lack of weight. Why 0.38 G? Because this is the gravity level on Mars. After 1 year, more or less, 1 year of travel, the astronaut arrives on Mars and is not subjected to a gravity equivalent to the Earth, but to a low level of gravity. Also, this could have a detrimental effect on his health. And we have to consider that apart if the astronaut is sitting or standing inside the small centrifuge and it is at rest, if the astronaut is moving inside a high centrifuge, let's talk about a spacecraft which is spinning. This is a big centrifuge. In this case, the gravity gradient is probably not perceived as a big problem, but there is also an effect induced by the Coriolis force, because if a body is moving with a velocity v inside a rotating system having an angular velocity omega, it is subjected to an acceleration which is given by the cross product of these two vectors. And we note that this acceleration is independent on the radius. It is the same and depends, of course, only, apart from the velocity of the body, only from the angular velocity. Okay? And this is also a problem because it could play a role in causing the onset of the spatial motion sickness we have studied 2 lessons ago. Of course, in the presence of a centrifuge, the astronaut, would be subjected to both the Coriolis force as well as to the centrifugal force. And it is important to note that the Coriolis forces are able to generate angular accelerations inside the semicircular canals of our vestibular system. And as soon as the head of the astronaut is turned out of the rotation plane, there are problems, for instance, in the correlation between movement of the head and of the eye in order to observe a trajectory of a moving object, because we have seen that the brain regulates the movement of the head thanks to the vestibular system. If this is solicited by this kind of acceleration and gives a wrong answer, also the brain can lose partially the correlation, and therefore the astronaut can have disturbances in the visions of moving object. Therefore, the results indicate that Coriolis force should be minimized in order to mitigate the problems induced by unavoidable head movements of the astronauts. Also, training pre-flight in order to accustom the astronaut to move in a slow manner his head could be useful in order to minimize this effect of motion sickness. Okay. Thanks to all these considerations, it is possible to define a so-called comfort zone for a combination of radii and corresponding angular velocities in order to obtain a zone in which the detrimental effects of partial lack of weight are overcome. Okay, of course, this is valid only for large centrifuges. So only if we decide to spin the spacecraft, because you can observe that the comfort zone requires a radius larger than 10 meters. So it cannot be applied to small centrifuge. Okay, what about the design? Having established that a pseudo-gravity force is induced by the centrifugal acceleration, we can think to two different routes in order to achieve this result. Either we use a continuous artificial gravity by spacecraft with large radius which are continuously spinning, or we use intermittent gravity using a small centrifuge inside a normal spacecraft which is simply translating. And concerning the spinning vehicles, the first technical proposal was made many years ago by von Braun, and this is a pictorial representation of his proposal. That is a spacecraft which is circular and which is spinning around the corresponding axis of rotation, inducing a pseudogravity along its circumference. But it is also interesting to point out that this was the first technical proposal, because more than 100 years ago, a Russian writer, which was a visionary in the sense of a forerunner, whose name was Tsiolkovsky, in 1883 wrote a book. He envisages space flight and realized that sufficiently far from the Earth, the astronaut would be subjected to weightlessness. And therefore, he proposed, or he already proposed, to spin the spacecraft in order to induce an artificial gravity. And this book remained unknown until 1956. Okay, just for historical curiosity. And concerning big centrifuges, spacecraft which are spinning, the basic configurations which are considered are the I, Y, and toroidal configuration. These are the schematic drawings. Of course, the last two are better concerning the stabilization, and the first one is the best in order to be launched, because there are also problems of weight and the need to probably to build the different pieces of the spacecraft on orbit. And this is a pictorial representation of a study of NASA in 1979 using the first configuration, the I configuration. And of course, there are also technical problems, huge technical problems in order to design a suitable propulsion system in order to not only to spin the spacecraft, but also to spin up and spin down, because in landing and in launching, for instance, to and from Mars, we need to change the angular velocity. And one possible solution for the I configuration is the so-called rigid truss. It provides a suitable counterweight on the opposite part with respect to the real spacecraft, which are connected by a truss. And alternatively, a telescopic boom could change the radius of the system in order to launch it and then to reach the final configuration on orbit. The problem of this kind of project is the weight. The counterweight must have a weight comparable to that of the spacecraft, and therefore, furthermore, there is also the weight of the connection, and the corresponding power is much higher, of course. Probably the so-called tether system is the most promising design. It was already demonstrated its feasibility during the Gemini 11 mission, because the capsule was connected to a booster with a 30-meter rope and put in a slow rotation, and the astronaut felt a small amount of gravity. And a variable length tether could be unreeled once in orbit, and not necessarily on launching, in order to connect the spacecraft to a counterweight. And a project of the NASA, just a very schematic drawing, provides a module of about 80 tons and a counterweight lighter, 44 tons. Of course, the center of mass is not in the center of the system, of course. It is displayed toward the module. And this would have the great advantage that the weight of the tether would be just around 2.5 tons. But of course, the drawback is the fact that a tether may be subjected to break more than the other solution, the truss. And we have why breaking? Because there are also asteroids who could arrive against this tether. And we have also to consider the fact that we have seen that not only humans, but every system in deep space is subjected to a high level of radiation dose, and radiation acts on the materials in order to make them brittle with time and with radiation dose. So brittling means that they are more fragile, and the risk of breaking increases with time. So this kind of project must take particular care also on the choice of the materials. Okay. What about small centrifuge? In this case, we must rely on intermittent artificial gravity, because it is not thinkable that the astronauts continue to rotate inside the small centrifuge for the whole duration of the travel. But this small centrifuge could be inserted inside a spacecraft without big problems. they would allow the spacecraft to continue to fly without rotating, so a pure translation motion. And of course, the big drawback would be that high rotation rates would be needed in order to reach a level of pseudogravity which is comparable to that on Earth, and therefore corresponding space motion sickness. But the hope is that the body of the astronaut could adapt also to this level. We have seen that space motion sickness is typical for astronauts in the first days of a space mission, independently on the duration, but the symptoms are disappearing after a few days. So the idea is that also in this case there is a sort of adaptation. But there would be a lot of advantages. Apart from the space which is spared, there are different projects which propose that the power for the centrifuge is supplied by the astronaut themselves. In this case, they could make at the same time exercises, aerobic exercises, and being subjected to the centrifugal force, and therefore a pseudogravity. This is a proposed model by NASA. It is called the human-powered centrifuge. It is formed by two astronauts who are moving their legs like cycling, but supine, and thanks to this movement, the centrifuge is rotating. This rotation could be increased by the presence of a third astronaut moving with a bicycle, which is connected, mechanically connected to the centrifuge. In this case, of course, they could combine the feeling of a pseudogravity together with exercise, aerobic exercise. And another system which requires the use of bicycle is a proposal by Italian scientists. It is called the so-called twin bike system. That is, two bicycles which are mechanically coupled each other and counter-rotating inside the cage. This reminds such gadgets of a cage with a hamster which is rotating inside it. But this would have the advantage, of course, to exercise the astronaut and have beneficial effects not only on muscles and bones, but also on cardiac system. So, as you see, there are several proposals, technical problems, but after solving these technical problems, this could be probably the best route in order to overcome all these troubles induced by the lack of weight. I have finished for the moment, in the sense that we will continue our lessons tomorrow and the day after tomorrow, but in the end of these lessons of lack of weight, I would like to leave you the message of let me say, the gravity of the situation for an astronaut performing a long travel without gravity. Okay, see you tomorrow.